Now we're going to extend the chain rule. So in the previous video, we only had 2 dependent variables. In this video, we are going to consider 3 dependent variables. 1, 2, 3. So in the previous video, with 2 dependent variables, x, y, and z, with two dependent variables, the xy plane represents a domain. But in our case now, we've got 3 dependent variables. So the whole 3D space represents our domain. And then let's say it's 1 and then 2 across and then 3 up. Let's say this point here, 1, 2, 3. So this is our domain here. If you put it into our machine, it will then jump to a value w somewhere over here. Let's imagine it jumps to the number 3. So here our situation is that we've got this function here with 3 variables, but it's driven by 1 variable. Let's imagine it as time. So as time ticks away, so all that's being inputted into our machine is just the time. You input a time, and then the time will then tell you where the particles should be in the x, y, and z direction. Once you've got your x, y, and z, then it will spit out a number. Let's say 3 here. So our job is to work out dw by dt evaluated at t equals 0. So our job is to compute this value here. Okay, so this is our situation at the moment. This is what our function looks like, and the 3D space represents our domain, and then from the domain it will spit out a value w here. Our job is to find dw by dt. Okay, so now extending the chain rule to 3 variables, it will look like this. So the chain rule will look like this, because you've got to consider you moving in the x direction, you moving in the x direction, you moving in the y direction, you moving in the z direction. So to compute dw by dt, we've got to take the partial derivative of w with respect to x. So let's look at this. To compute this thing here, we need to differentiate it with respect to x. So x is our variable, everything else will be constant. So y will be a constant, z will be a constant. So when you differentiate this with respect to x, it just simply becomes y squared. It just simply becomes y squared, because this is just a constant. So this whole block here is just a constant. So when you come to differentiate it, it disappears. Now we've got to times the derivative of dx. Well, we've got to find dx by dt. So dx by dt is minus sine of t, and then now let's look at this bit here. We've got to look at this and differentiate it with respect to y. So x will be a constant, z will be a constant. So when you differentiate this with respect to y, the 2 will come down, so that will be 2. X is just a constant, and then y stays the same, and then the power gets minus by 1, so to the power of 1, and then times dy by dt. So dy by dt is right here. Differentiate that will then give you cos of t, and then now find differentiate it with respect to z. So z, well, this is a constant, this is a constant, making the whole thing a constant. If you're differentiating it with respect to z, it just becomes 3. It just becomes 3, and then multiply that with dz by dt, which is 1. So it becomes 1, and then from here now we've got to evaluate it at time t equals 0. Well, what is y at time equals 0? Well, at time equals 0, y, well, put 0 into the t here. So sine of t, sine of 0 will be 0. So y will be 0, meaning y squared will be 0. So this thing here will be 0 when you evaluate it at t equals 0. So the whole thing here, 0 times whatever this thing is just going to disappear. And then what is x at time equals 0? X equals 1 when time equals 0. So this x here is 1. What is y when time equals 0? Well, sine, we just established that sine when t equals 0, sine would be 0. So this will be 0. Then the whole thing would be 0. And then, well, dw by dt equals 3. Okay, so that's your final answer here. It equals 3.